In this tutorial, we're going to continue discussing the take-up inputs and outputs, only we're going to focus on the different take-up types, the difference between a gravity take-up, a fixed take-up, and the automatic winch control. Again, you might want to refer back to your SEMA manual or your conveyor design manual for some of the fundamental basics of those calculations. And so on and so forth, because I don't want to get into those in detail. In these tutorials, I want to focus on how you use Sidewinder and what the input and outputs mean. So you might want to just re-reference that. Again, if you also just put your cursor over any of the inputs, like the take-up type here, it'll give a short little description, or you can refer back to the user manual. But we're working again with the same tutorial that we've been working with. Again, this is this decline-incline conveyor. We've got a gravity take-up at the head. And as we went through on the previous take-up tutorial, when I leave the belt tension blank, Sidewinder has selected a take-up tension of 62.7 kilonewtons. I'm going to actually go ahead and just put that in there so it stays fixed for us as we go through some of these different take-up tensions. We'll let it select in a minute here. But when I run the calculations, we can go to our take-up tension here, and we can look at our empty belt case. And you'll notice that there's these two lines here I want to focus on. First is the tension, and this is the belt line tension at the take-up. And you notice it's the exact same for all cases. Operational stop, starting, running, so on and so forth. And the second line is our take-up pulley our displacement. Now, Sidewinder always assumes that the steady state running empty belt condition, that's our zero take-up pulley position. So from that position, when we go from empty to fully loaded, we can see that the pulley is essentially dropped by 0.1 meter, 100 millimeters. And if you're always wondering about the which way the displacement is, which way positive or negative is, if you click the All tab here and you just look at the picture, it's always shown on the image. Sidewinder assumes that contraction of the belt, or the pulley moving up in a vertical take-up system, would be a positive displacement, and moving down is a negative direction, or stretching of the belt is a negative displacement. So what's actually happened with the belt when we went from full to empty? We've had two things happen. If we can imagine when the conveyor is running empty, the conveyor link has some links to it. It's sitting there running empty. Now we load the conveyor. Well, if we forget about the tension change for a second, we just think about the load on the conveyor. The load on the conveyor is going to cause the belt to sag in between each of the idlers. Okay? So since the belt is now sagging between all these idlers, our gravity take-up has to move up. Our belt has to contract at the take-up, because we're taking more belt out in between the idlers, so it has to go somewhere, which causes our take-up pulley to move up. Now, opposite of that, if we say, okay, let's forget about the belt sagging between the idlers when we load it. When we load the belt, for most conveyors, or let's just talk about a flat conveyor or incline conveyor, from the empty case to the fully loaded case, the tensions in the belt increase. Well, since the tensions increase, the belt stretches. So in that case, we start with our empty belt. We've got some link to it. And now we increase our tension while our belt is stretching. Well, because it's stretching, the take-up actually drops. So it's the combination, it's the summation of those two. In one, the stretch of the belt is causing the take-up pulley to drop. The additional sag between the idlers is causing the take-up to rise. So in this case, the summation of those two results in a total pulley displacement change of about 100 millimeters, 0.1 meters it's dropped. Now also in the running condition, or when we go to start this fully loaded conveyor, we can see that the take-up has dropped actually 0.4 meters, and that makes sense. If you've got your conveyor that's sitting there, stopped, and you go to start your conveyor, your T1 tensions are increasing, essentially stretching the belt on the carry side, and that stretch is going to a lower T2 tension on the other side, which is causing your take-up pulley to drop. In this case, the starting is causing it to drop about 400 millimeters, 0.4 meters. And for the operational stopping condition, it's just actually the opposite. It's causing the take-up to actually go up 1.2 meter. So that's what this is all about here. I mean, this is the basics of our conveyor design. Now, what happens when we go, switching back to our empty case here, when I change from a gravity to a fixed takeup? When I switch this to a fixed takeup and I hit run, we can see that our empty belt steady state running tension is still 62.7. We also see that our empty belt takeup pulley displacement is also still 0. That is our reference point. So that value that we enter now for the fixed takeup, that's going to be the value for the empty belt steady state running. But in this case, now we've got a fixed takeup. So whether the belt is empty or full or the inclines or whatever case you want to select, you see that the pulley displacement is now 0. We've got a fixed pulley. So since the pulley can't change, the belt length is essentially locked in place, what changes is the tension at the takeup. So when we're empty, that tension is what we specified here, 62.7. But when we're loaded, that tension is actually dropped to 62.0 roughly. When we're starting, the tension is actually dropped to 58.2 kilonewtons at the takeup during starting. During the stopping, it's increased 75 kilonewtons. So that's the fundamental basic difference between the gravity and the fixed takeup. With the gravity takeup, when we run it, our tensions obviously stay constant, but our displacements change. When we go to a fixed takeup and run it, our displacements are constant, but our tensions are changing. That's it. It's that simple. Now, we also have an automatic winch control system. The automatic winch control calcs are almost identical, or basically identical to the fixed takeup. However, what the automatic winch control says is it says, okay, when the conveyor is running steady state, even though we might have an incline load or a decline, and those might only be momentary conditions, the basis of this calculation is that during steady state running, that running tension or the takeup will adjust to whatever tension we enter here. So our empty case, which is 62.7, if I go ahead and run this, is 62.7. Now our fully loaded case is also still 62.7. Even though the pulley's now moved, it's 62.7. Incline, the pulley's moved again, but that running tension is 62.7. Decline, 62.7, so on and so forth. So we're still doing rigid body dynamic calculations here. We're not doing flexible dynamic calculations. But for the rigid calculations, it's assuming that the running tension, it will now adjust the running tension for each of your load cases to match that belt line tension. Now, in that case, if we take like the fully loaded case, for example, the pulley has, or the takeup has adjusted to 62.7 and minus 0.1 meter. Now for that case, for the dynamic conditions, it assumes that this is a fixed takeup system. So it adjusts for the running case, but for all your dynamic conditions, it then assumes that it's fixed. So it's pretty neat, pretty powerful little option that you can essentially simulate a automatic winch control in that respect. Again, just reiterating, and I don't want to make this tutorial too long, but if I go to a fixed and I run it, you see on the empty case I've got a running tension of 62.7, but I go to the loaded case, it's 62.0 or whatever it happens to be, because my pulley is not moving. If I go change this to an automatic and run it, you'll see it's 62.7 for all running cases. But once you hit that running case, now your displacement is fixed. Now there's one other just minor note on automatic winch control, and that's that we did have a lot of users that actually asked, hey, we love the automatic winch control, but can we also add a pre-starting tension? Because our conveyor is running, and yes, we've got a running set point for that conveyor that's, whatever, 62.7 kilonewtons. But before we go to start the conveyor, regardless of what the loading on the conveyor is, we pre-tension that winch to a specific point, and you can do that. So, for example, if I put in 80,000 here for a belt line pre-tension starting tension, and I run it, you'll see that now for the full case, we've got 62.7. The only difference is our starting case now, we've pre-tensioned it to 80 kilonewtons. Okay, and that'll be the same for all cases: empty, full, inclines, declines. So it's essentially like running a separate fixed take-up calculation, but adjusting it just for that starting condition. So in other words, if your belt's fully loaded, what the take-up would do is it would actually displace minus 2.1 meters for this conveyor to bring the tension up to 80 kilonewtons, and then from there we'll accelerate the conveyor and we'll do all the calculations. Then we assume that the conveyor is now running during steady state. That take-up has now moved back to our target tension of 62.7, which happens to put the pulley at minus 0.1 meter, and that's where it's running at for the steady state running. And then when we go to stop it, whether it be an operational stop or emergency stop, that pulley is fixed at that position and our belt tensions change. So, all right, I think that wraps it up for this tutorial. Hopefully that cleared up some things. I know there's a lot of information there and a lot to digest, but it really shows you the power of Sidewinder. Just one last note: if I go to the fixed take-up here, I know we had started with a take-up of, we had specified a take-up, but just like the gravity case, I can go ahead and leave that tension blank and run the calculations, and Sidewinder will automatically go through and pick the worst case scenario for me. In this case, it picked a take-up tension of 76 kilonewtons. Again, that's 76 kilonewtons for the empty belt running condition. If I look at the fully loaded condition, and we look at our fully, we see that our running tension is actually 75.6 kilonewtons in this case, which is obviously different. Because we've got a fixed take-up. Again, the pulley's not moving, the tensions change. But the point I wanted to make was, in the green output window here, the values that you see here, these are the values that you would enter here to meet these requirements. In other words, if I go through these cases, okay, we needed 46.4 for sag. For the incline case, hey, we needed a empty belt steady state running tension with a fixed take-up of 71.2 kilonewtons. Okay, that looks like, I think, yep, that's our design case. Again, like with the gravity, and we discussed this in the previous tutorial, Sidewinder then adds about 5% on top of that, and thus we ended up, Sidewinder automatically picked and rounded it to 76 kilonewtons. So, pretty slick, pretty powerful.